Anthony. So,
Thank you.
so thank you again. And then we move to Jelmer. Jelmer is an assistant professor at the TU Twente, and he has been doing some really wonderful work on applying geometric deep learning concepts like graph neural nets to problems in medical image analysis, and he'll talk about this now.
Yes, thanks for the introduction, Max, and thanks for the invitation to be here. I hope I'm sharing the right screen.
Yes, you are fine.
Okay, good. Yeah, so like Max said, I'm Jelmer Wolterink. I'm an assistant professor in Twente, and much of the work I will share today was done at Amsterdam UC and UC Utrecht, where I was previously. And this will be very much more an applied talk to give some examples on how geometric deep learning and mostly graph neural networks, graph convolutional networks can be used in the analysis of medical images of patients with cardiovascular disease. And I assume that not everyone is familiar with cardiovascular disease, so I will take a step back and give a brief introduction to that here. Okay, so cardiovascular disease is actually an umbrella term for diseases affecting the cardiovascular system. So you see this very nice rendering here on the right, where you see the heart and then the arteries in red and the veins in blue. And this whole system can be affected by different kinds of diseases that will manifest as the buildup of plaque in the arteries, so the position of things that shouldn't be there in the vessel wall. And that can lead to, for example, stenosis or narrowing of the vessels. And you can imagine that if there's a stenosis somewhere in an artery that is supposed to supply an important organ with oxygenated blood, that can have major implications if that doesn't work anymore, like when the heart is not supplied with oxygenated blood or when something happens in the brain. And on the other hand, you have aneurysms, which mean that the vessel wall dilates or weakens and can at some point rupture. And two very common locations for these aneurysms are in the brain. And if an aneurysm in the brain rupture, this could lead to stroke that we've all probably seen. And if an aneurysm in the abdomen ruptures, where there is this large vessel, the aorta, it can lead to death in 80% of cases. So well, particularly clinicians want to know before something like that happens, where in the body this cardiovascular disease manifests itself. And luckily, there are all kinds of imaging modalities that can be used to provide non-invasively an image of the heart and the blood vessels. So you see three commonly used modalities over here. On the left, there is CT, which has high spatial resolution, and you can very clearly see the relatively small coronary arteries there, which have a diameter of 1 to 6 millimeters. What has the drawback that you need ionizing radiation. And in the center, you see an MRI scanner with an MRI image on top. This is a cardiac CMR image, which provides also some temporal information, because you really see a video here of the heart beating through the cardiac cycle, and does not use any ionizing radiation. And on the right, you see an ultrasound image acquired with an ultrasound probe, which you can imagine is a lot more mobile, transportable than a CT and an MR scanner, which is used a lot to image vessels like the carotid arteries that you see here, and also abdominal arteries. And these modalities are used a lot in combination with others like SPECT and PET, and result in thousands and if not millions of images that all need to be analyzed in a way. And that's what the field of medical image analysis is about, and which has been transformed hugely, like all fields involving imaging in the past couple of years, by deep learning. So this is a figure from a paper that we, review paper that we wrote 2 years ago already, where you see some applications of machine learning, deep learning in cardiovascular imaging. So on the top left, you see image analysis in OCT. So this is a minimally invasive procedure where you actually insert a catheter in the artery and you try to find out what's going on inside the vessel wall. Then you see an image below from a paper by Nicolas Lesman who's now in Nijmegen, on calcium scoring, so identifying voxels that are calcified in the coronary arteries. And this could be used to make a prognosis for patients with coronary artery disease. At the bottom you see a SPECT image, which is a nuclear image that can be used to detect if someone is suffering from coronary artery disease or not. And on the top right you see an ultrasound image, and on the right here you see a left ventricle segmentation in an MR image. And all of these things would be very time consuming and strenuous for a clinician to annotate, but with deep learning we see that these things work really well and really fast. So in general there's a lot of enthusiasm and interest in these techniques from clinical specialisms that work with images. And in particular in cardiovascular imaging, so this is a figure from a review paper by Tim from Utrecht that shows that machine learning is expected to have an impact on all steps that a patient goes through in the cardiovascular imaging pipeline. So acquisition of images, new sequences might be developed at some point, CT scanning protocols could be optimized using machine learning, image reconstruction, so there's a lot of work in MR reconstruction and CT reconstruction aimed at reducing the time needed to make an image and reducing the dose needed to make an image in CT. And there's more and more a shift there from using purely data-driven methods to also including the decades of research on model-driven reconstruction. And then the vast majority of deep learning work in cardiovascular imaging has been in segmentation and quantification. So there is an image, and where the image is the object that I'm interested in, where is this particular organ, or where is this plaque or pathology. But as I will show you also today, there is also a part to play for deep learning in classification and reporting and in prognosis. So based on information in the images and maybe other information, can you give a prognosis for a patient, how the patient will be in 5 or 10 years, and how serious the condition is. Now the whole deep learning boom in medical imaging has been mostly driven by convolutional neural networks, which makes a lot of sense because reconstructed medical images come on 2D and 3D grids. So the marriage between convolutional neural networks and medical imaging is a very natural one. But there's also a lot of information that we may want to deduct in a second step, or either directly from medical images, that is better represented as graphs or meshes. And that is what this talk will be about today. I will show you some examples of this relatively new direction in deep learning in medical imaging, of where the problem can be best described as learning on a graph or on a mesh, and how we can use techniques in graph convolutional networks and mesh convolutional networks for that. Yeah, so like I said, CNNs work well on regular grids, but as you may be aware, the operations that make a CNN, like convolutions and pooling, they don't generalize too well to graphs and meshes. So imagine that you have a graph now instead of a rectangular grid, then there is not really a particular order in the nodes, as you assume there is if you do a convolution on an image. And you never have, not necessarily have the same number of nodes or neighbor nodes for each node. So convolution kernels have to be quite flexible. And luckily, there's been a lot of work in graph neural networks over the past few years. So you see an abstract graph neural network here at the bottom left. But the applications include, for example, social networks, molecules, which I think the third speaker today will tell us a bit more about. And then there's also a lot of interest recently in mesh convolutional neural networks, or using graph neural networks on meshes and making predictions on these meshes. So in this case, which vertex of this mesh corresponds to which body part. And in medical imaging, we're not necessarily, with some exceptions, interested in the outside, but we really want to look inside and use these techniques to learn more about what is going on inside the patient. And one particular example where graph neural networks are a natural choice is vessel tree labeling. So on the left here you see a very abstract image of how arteries and veins are organized in the body. And with some exceptions, arteries always start from a larger artery, which is the aorta, and then branch off in many different directions. And there's a very complex branching pattern. But in principle, over hundreds of years, names have been given to all of these segments, and we're interested in, if we find something in the human body, where exactly this is found, and if that can be reported back, for example, to the clinician, or if the exact location or the segment that something is found in could maybe be used in a follow-up model where we do prognosis. Because not all the locations that we can find something in are equally important. So you see on the right an example of just a subset of names for arteries and veins in the body. And what we are particularly interested in are the coronary arteries. And this is actually work by Niels Hampe, who presented this last week at SPE Medical Imaging and was also nominated for the Best Student paper there on work for automatic coronary segment labeling. So you see here an image of the heart with the different heart chambers shown in different colors. And in purple you see the myocardium, which is actually the thing that contracts to pump blood through the body. And the red things that you see here are the coronary arteries. And if something is identified, like coronary calcification or some other pathology in these coronary arteries, it is also important where in the coronary artery it is actually located. Because you can imagine that if something is located quite distally, so for example here at the bottom in this very narrow vessel, it may be less dangerous than when something is located here in the left main artery. So a problem that people have been working on is coronary segment labeling, where for each of these segments, you provide a label according to some anatomical model. And it's really a matching problem where you have many different patients and an anatomical model, and you try to find a match between a segment in this patient and that patient, for example, patient, that patient. And you already see that this is quite a challenging problem because in 3D, these trees look quite different. But also if you straighten them out, you see that, that some patients have many more branches than other patients, that the length of these vessels is never the same, and there are many problems. So what we try to do is map each segment to a predefined label in an idealized model, like you see here, like is used by cardiologists. But the challenges are that there is a lot of anatomical variation between patients, that there are abnormalities that can occur. So we always assume that there are two distinct coronary artery trees on the left and on the right side of the heart. But it could be that both originate from the same origin in the aorta. And then there's not always the same number of segments. So it could be that a patient just never developed a particular branch, that the branch is not visualized well in the CT image that we use to extract these, or that the automatic algorithm that we use to extract these just doesn't extract these well. And on the other hand, it could be that there are segments that don't fit the idealized model. Still, we went for it, and in particular Niels. And as input there, he used a graph, a tree graph of automatically extracted coronary artery centerlines. So we developed previously an algorithm that takes a CT scan and then follows the centerline. And by applying that multiple times with different seeds, you can build a graph like on the right here. And then with some simple post-processing, you can extract separate segments and bifurcation points. And that is actually the input to the automatic tree labeling algorithm. And on the left, you see this, this input. We have to straighten it a little bit, and out comes a graph like this. Remember that we don't really know the segment labels yet. And also that each graph is actually different for different patients, depending on the number of branches that are visible and identified. And in a graph like this, there is a number of nodes. So there are nodes at the ostia, or the origins of the coronary artery trees. There are nodes at the branching points, at the bifurcations. And then there are nodes at the leaves of the artery trees. And here the edges are actually made up by the segments. So one thing that we did here was actually change this representation, because we are not interested in labeling the nodes or the bifurcations per se. We were interested in labeling the edges in this case. So we made a line graph where the nodes actually were replaced with edges, and the edges were replaced with nodes. So for each edge in the original graph, a node was placed, as you see here. And for each combination of segments or edges in the original graph, which was connected via a node or a bifurcation, the original graph, an edge was added. So that's why this looks a bit weird, this graph on the right. But the benefit of using this line graph is that we can now perform graph convolutional network with the nodes as or actual vertices, or the segments as their actual vertices. So as a next step here, features were defined that are used to build a graph convolutional network. And these were just handcrafted features based on anatomical knowledge and based on the original location of these segments that are now vertices in the tree. So these are positional features relating the position of each segment to a central point in the myocardium that you see over here, the depth of the segment in the tree, and then the mean and standard deviation of the segment radii. You can imagine that a larger segment or a wider segment is more likely to be closer to the ostia, and a smaller segment is more likely to have the label of a more distal segment. And then for the graph convolutional part, the features need to be combined and information needs to be exchanged on this graph between the different neighbor nodes. And for this, we used a graph attention network, which is quite a standard graph convolutional layer, which uses a trainable weight matrix per layer to transform the previous feature vector into a new feature vector, just like in a normal linear layer in a convolution in a normal neural network. And then has this alpha vector here, which is a attention parameter that says how much each of the nodes in the neighborhood of a node V. So we see that there is a one ring neighborhood here around the node V. How much each of these nodes contributes to the new feature representation of the node V. And this is actually a learnable parameter, and all the attention factors for a node sum up to 1, so that the input to the nonlinearity in the end here is always at the same scale. So in this case, we stacked 3 of these graph attention layers, used dense connections to make sure that the input features were also used in the second and in the third layer as input, and then a softmax layer performed a 10-class classification into these 10 different segment classes. So as an experiment, Niels made sure to have correct reference standards in 71 patients, which was a combination of automatically extracting an initial tree and then manually correcting here and there where parts were missing, and then performed a 10-fold cross-validation that in which 90% of the patients were used for training and 10% was used for testing. And you see here, and just a reminder what the graph convolutional network is supposed to do. It's supposed to assign for each of these segments in the original tree one of these 10 labels. Well, and this is a problem that people have been working on for a couple of years. So we can make a comparison to previous work, where it should be noted that unfortunately there's no standard data set here. So it's not a direct comparison, but we saw that compared to 3 previous methods, which follow more of a graph matching approach, where you first try to find the main coronary arteries, the left one and the right one, and then use a rule-based approach or a more model-driven approach to figure out what the label should be of all the branches, or a purely data-driven approach without any rule-based mechanism, performed quite well. So in red you see the proposed method, and in yellow, blue, and green you see the previous works, where the y-axis shows the precision or the positive predictive value, which means that, for example, for the left main, the graph neural network was maybe a bit overly optimistic and assigned that label sometimes incorrectly, whereas it did quite well for the LCX and for the diagonal branch, for example. What you also see here is that even among these different methods, there is not really a clear consensus about what should really be the segments that should be labeled. So, for example, we are the only method that labeled the acute marginal branch here, whereas the method by Gulson and our method was the only one who labeled the septal branch over here. And over the past 2 years, and even before, there have also been some people working on machine learning approaches to this, to more data-driven approaches. And we can also make a comparison to those. And in particular interest is the one shown in blue here, which considers the whole segment labeling thing in the tree to be a problem that's a problem of solving and a sequence of segments really, and uses an LSTM instead. And well, you see also here that it compares quite favorably. And just to show you one example of where the method got confused, is at the distal part of the left circumflex artery, where you see the reference over here, which shows that the curly thing here should be the LCX, whereas the yellow branch here is the obtuse marginal branch, which also corresponds to what you see here in the idealized model on the right. And the model instead labeled the obtuse marginal branch as the LCX and the remainder part of the LCX as the OM. Now, the potential of graph convolutional networks for vessel labeling has been picked up also by others. And this is a paper that appeared last year at CVPR, which follows a very similar approach using graph convolutional networks for labeling of each individual segment, but adds to that a layer of feature learning. So in addition to these handcrafted features that we use, also uses a BiLSTM using 3D CNN feature extractors to obtain better representations maybe of these coronary artery segments in 3D space, also based on the imaging information. And it's not only in the coronary arteries that people are interested in using graph convolutional networks for artery labeling, but also, if we move up a little bit, this is a paper from the MMI workshop at MICI last year, where graph convolutional networks were used in combination with point clouds to label the arteries in the head and neck. So you see the carotid arteries and a whole list of variants of the carotid arteries and other vertebral arteries, which were also automatically labeled with graph convolutional networks. Just because of the potential of these networks to find the relation between different segments and elements in the graph-like structure. And then this is another one, very interesting, where graph neural networks were used to make a distinction between 20 different arteries in the brain, and that you see here on the right. And this is also a very interesting problem because these are not necessarily organized in a tree like the coronary arteries are, but the brain also includes some circularity, like the circle of Willis here in yellow. And actually these authors in this paper which was presented at MICI last year collected a very large data set of 729 patients, including many patients with abnormalities. And in their paper they show how the graph neural networks are to some extent also robust to missing segments in the scans and also operate quite well in heavily diseased patients. And what's also interesting is that this is actually provided, this data set, as a publicly available data set. So if you're working on graph neural networks and you're tired of Cora and Sightseer and you want to try something new, you can download this 729 patient data set and have a go at it. And in this case, I think the authors used a encoder decoder GNN like architecture, which already performed quite well. So that is really about vessel labeling, where you really have a clearly defined label for each vessel. But another problem in vessel analysis is distinguishing between arteries and veins, and especially if you have a 2D projection of the blood vessels, like you do have in fundus images, and these vessels are actually projected on top of each other. It may be quite hard to separate what is an artery and what is a vein, where while the function of the two is quite different. So there has been a lot of CNN work on segmenting the blood vessels in the retinal images, and that works quite well. There was also an example in the previous talk of that using rotational equivariance. But here the authors propose to use graph convolutional networks in combination with CNNs to learn more about the relation between different pixels and where they stand in the coronary tree. So they used a graph UNet, which takes the multiscale aspect from the UNet using pooling layers and upsampling layers, and then considered each of the pixels in the vessel mask in the retinal images to be a vertex in this graph, and then label these vertices according to whether they are in the artery tree or in the venous tree. You see an example here on the right, where the graph convolution network is able to at least consistently label this whole thing as a part of the arterial tree, whereas the CNNs in the second and third and the fourth row here are a bit confused between the arterial and the venous tree here. And if you add a dimension to this, then you can also do things like this in 3D. In this work from Leiden, where you have a CT scan, you can extract a skeleton of all the blood vessels in the lungs, which are also closely intertwined arteries and veins. And you can use a CNN to extract locally features and then represent each of the pixels along your skeleton using these features, and then use a graph convolutional network to learn how to separate the artery tree and the venous tree here. And actually this also shows that, that whereas you can consider your graph to be a collection of segments of arteries or edges in arterial trees, you can also consider each pixel to be an individual individual sample. So this is really more of an overview of what has been done in this very clearly graph-like problem. But on a more general note, there's also some interesting work being done on segmentation in medical images, and finding the connection there between CNNs and graph convolutional networks. And that will actually be the second part of my talk now. So, as you may be aware, many problems in medical imaging involve segmentation. But for many many downstream tasks, we are not necessarily interested in finding a voxelized representation or a pixelized representation. But we want to have a manifold mesh. For example, if we want to run some simulation on our segmentation data, or we want to do some visualizations, or compute some features on the surface, it may be beneficial to have a mesh instead of a voxelized representation. But yet, commonly used methods like UNet, fully convolutional networks, VNet, they operate on a per pixel and per voxel level, and also give us a result which has the risk of containing holes or some spurious fragments. On the other hand, if we want to obtain a mesh from that, there's always a second stage that is required. So the CNN may give us some voxelized representation, and there is a post-processing step required that includes things like morphology, margin cube, surface editing to come up with a watertight mesh that can be used for other applications. This is a multi-stage process with multiple possibilities for errors, and a very interesting direction for graph neural networks and mesh convolutional neural networks in medical imaging is to see if you can directly obtain a mesh from the image without this intermediate step. And one problem where this is relevant is in the segmentation of small vessels from medical images, where we want to know exactly where the vessel wall is in 3D. We want a watertight manifold mesh segmentation because we know that in fact the blood vessels are also watertight if all is well in a manifold mesh. And using meshes as representation gives us one structure without holes or false positives. It allows subvoxel accuracy, so we can let go of the voxel coordinate system and really use the world coordinate system here. Meshes are memory efficient and they can handle the sparseness quite well, also these very small structures in 3D. An added benefit is that if we use a mesh, we can also use an initialization that's based on a prior, so something that we know really about the object that we're trying to find. So in this case, for the problem of finding these coronary arteries, we use a tubular prior because we know that the blood vessel is in fact a tube. And if we initialize our tubes well, then all we have to do is deform the wall of the tube so that it matches really the vessel wall that we see in the 3D medical image. And for the initialization, we were lucky enough to already have the centerline extracted from the medical images with the previously described deep learning method. And we get a tube like this, and then the goal is to deform this tube so that it matches exactly the anatomical coronary lumen wall. And locally, we can represent this tube as a mesh, and we can directly operate on this mesh using graph neural networks. So that's what we did in this work, where the goal was to find the mesh vertices in the 3D space. And we did this based on this centerline that was already available, based on this tubular prior around the centerline and then the deformation of this tube so that it meshes. Using a graph neural network that directly operates on the mesh, that gives us then a watertight mesh with subvoxel accuracy. So the representation here is based on the centerline that we have. So we initialize this mesh around the centerline where each mesh point or each mesh vertex is defined by this fixed centerline point. Then orthogonal to the centerline, we place a contour. And in this contour, there is a second parameter, the angle, which actually only matters to define what the neighbors are on the mesh and does not really have a meaning in itself. And then there is a third parameter, which is actually the one that we try to predict and the one that really determines what the mesh looks like. And that's the R, the deformation, or the distance from the centerline point. So if you look at this cross-section here of the vessel, you see that there is some calcium here that we want to exclude from the lumen. And using this separate R value per angle, we can have a very flexible contour here that is just circular over here and then has this dent over here. And the whole goal here is to go from an image to a mesh directly. So as input features for the prediction of each R for each vertex, we actually use image intensity values that are extracted along a ray cast from the centerline point through the angle phi, and that's used as the feature factor xp.
So Jelmer, there's about 5 minutes left.
Okay.
Yes.
Excellent. So, well, we can go over this relatively quickly. This is a graph neural network layer that we used, which is based on the graph stage layer, where you have, again, a neighborhood, a one-ring neighborhood for each vertex phi. And you combine the information from the different neighbors in 4 steps. Again, send and receive the representations, aggregate those using a mean operation, and then use those, use trainable weights just like in a normal linear layer to obtain new features and pass those through a nonlinearity. And again, here we use a 3-layer graph convolutional network where you see that by adding these layers, we increase the receptor field on the mesh that is used to make a prediction for an individual vertex. And we evaluated this in a public evaluation framework where segmentations are provided, and we can run a leave one out patient cross-validation so that we actually train with the manually annotated segments and the manually annotated center lines, but we test on a completely automatically extracted center line or coronary tree and predict the vessel wall there. But that leads to quite good results. So in this table, we show two of the best performing automatic methods, the human observer, and then at the bottom, the graph network, which has both high overlap with the reference annotations and a good and relatively low mean surface distance with the representations. If you compare that with a multi-layer perceptron, in which we have exactly the same number of parameters, but we don't have this information exchange between neighboring nodes, we get a much more irregular segmentation, and which just shows the benefit of using these graph convolutional networks here. Then one thing I still want to show is that there is now also a more move to extracting meshes from images by really using a combination of priors and encoder-decoder schemes that we all know from UNet, like image analysis methods. So this is a figure from a paper that uses a voxel to mesh-based approach, where you have an image coming in. There is an image encoding module, just like we have in a normal segmentation unit. There is a segmentation module that is able to provide a occupancy mask of the heart here. But the interesting part is going on at the bottom here, where there is an initialization of a couple of spheres, each corresponding to a heart chamber. And then just like in a normal decoder, there is an increase of resolution or in each step, where actually the deformation of the vertices is predicted, using a combination of a graph convolutional network and these image features extracted in the image encoding module. And at the end, what comes out should be a watertight mesh for each of these heart chambers that using a mesh-based loss is optimized to actually give a good segmentation. And this image from that paper shows exactly why it would be beneficial to use voxel to mesh approaches in some cases. So especially at the bottom row here, you see the results for a UNet in 2D and a UNet in 3D. And you see that there is not really consistency, and that the structures are not really contiguous. So there is this pulmonary artery here shown in red, which is then intersected by a part of what I think is the left atrium here, whereas the meshes actually give you contiguous structures. And that's also reflected in the numbers that are shown in this paper in terms of dice overlap. I think this is a very promising direction for geometric deep learning medical imaging. The question is what to do if you have these meshes. We can do the things that we all do, like visualization, quantifying volumes, and computing area-based statistics, and using simulations like FFR, as you see on the right. Or you can actually try to do more deep learning on these meshes. So two examples. So one example here is using the segmentations and graph neural networks that you can get from a myocardial segmentation in cardiac MR to predict motion over time and to extract motion parameters that can then be used to detect if a patient has some abnormality in the way that the heart moves. Another very interesting example is here, where the geometric information is extracted from a cardiac MR image and then represented here in a mesh, combined with some global information extracted from an ECG, and some known information about activity in the heart, and then used in a graph convolutional network which uses SAGE layers to and actually predict on the surface mesh of the heart where the electrophysiological activity is at some point. And this is really an example of using graph neural networks to operate and to learn on meshes. And I think there's a lot of potential for this, but in order to do that well, we also need some new methods and look maybe towards developments in computer graphics. And two important things that we need there are to consider that triangular meshes are not the same as graphs. So the things that we like about graph neural networks, like the permutation invariance and the flexibility to different numbers of nodes, may not be optimal for operating on meshes, because actually structure matters and spatial locations matter. And we need mesh DNNs that can give us anisotropic filters. So this is an image from a paper by Pim de Haan and Taco Cohen, Max Welling, on the why we need anisotropic filters, because we want to be able to distinguish on a mesh in 3D that these are actually different local neighborhoods. So we need to take into account that this angle is different in this example and this example. Or we need to consider specific features for nodes or for edges that are invariant to translations, invariant to rotations of the mesh. Or on the other hand, we want things to be equivariant. So there's a whole new field of combining these developments and what we're interested in learning from our medical meshes. So to summarize, deep learning has had a huge impact on medical imaging over the past few years. CNNs have been very successful, but are not necessarily the go-to situation or a solution for each problem. We may have to look towards geometric deep learning and particular methods working on graphs and meshes, which have many opportunities in different steps of the pipeline. And one thing that I think is very promising is to combine really the CNN for the image analysis side and extracting the useful representation from the images, and then the graph convolutional networks to give us the meshes or the graphs that we're interested in. And that concludes my talk, and I'm happy to take any questions.
Thank you very much, Jelmer, for a super inspiring talk. Very nice on topic also, geometric deep learning for medical image analysis. Yeah, so I want to open the floor for some questions. Again, please put your question into the Q&A box. I don't know precisely which one was placed in the box for which talk, so please add some new ones and not in the chat. Or speak up or raise your hand, then we can unmute you.
Is it mine? I see a question that could be for me.
Oh yeah, go for it.
But Faisal Diaz, who asked if there are any pre-trained graph convolutional networks available for medical imaging. And actually, I don't think we're at that stage yet with graph convolutional networks in medical imaging. So there are not really any networks that I am aware of. And the question is also a bit if, given the flexibility that you have in your graphs and your meshes, if pre-trained graph neural networks are going to be very valuable if you want to apply it to a new problem. What resources that are useful, of course, are the large data set that I mentioned on artery labeling.
And there's another one then, or no? Oh no, that's okay. Oh, that's AM. Okay. Funny ordering of the messages, I guess. So do you think uncertainty prediction is useful for these kinds of tasks?
Oh yes, absolutely. I think uncertainty prediction is always important, especially if you have these high stakes tasks. And already in the vessel labeling, for example, if you can provide some report, and you can also provide how sure you are that something is actually in one coronary artery or another coronary artery, that could be relevant. But also if you operate on these meshes, or if you, for example, make a segmentation and you want to know how sure you are of the segmentation. So I think all of these issues that are being addressed with convolutional neural networks are also very relevant for graph convolutional networks.
Yeah. More questions? Okay, if not, then we'll take our little break. So we have a 15-minute break until 4 o'clock European time. And then at strict at 4, we will start with a keynote by Marinka Zitnik. Jelmer, thank you once again for a wonderful talk. And then I will see everybody back in 15 minutes.